Metro Denver chapter of CRES, our June speaker series. We are so excited to have you here. Before we get to the main presentation, I have a few announcements for you this evening. So as a reminder to those who have joined, or as an announcement to those who have not, our mission here at the Denver chapter is to support a 100% renewable Colorado through education, engagement, and connection to networking opportunities across all Denver communities. So I'm going to go through a few announcements tonight, then I will turn it over to our Director of Policy, Johnny Rogers, for a few updates on the policy side. So if you have any feedback for us, we would love to hear it. You can do so in a few ways. If you have any questions tonight, feel free to send us a question through the question box. We will get to it at the end if there is time. We'd love to hear from you. Feel free to type your questions throughout, but we will hold all questions for the end. And then beyond that, if you have any feedback for us, we would love to hear it. You can send us an email at mdcres@cres-energy.org. We would love to hear from you there. And if you'd like to support us in other ways, we would love and appreciate that. You can donate to support CRES online at our website, which is www.cres-energy.org. You can Venmo us at MDCRES, or you can change your charity of choice on Amazon Smile to donate a little bit to us every time you shop online. And another great announcement for you, this year is the 25th anniversary of the Colorado Renewable Energy Society, and we are offering 25% off all annual memberships. So encourage you to check that out if you have not already done so. The promo code is CRES, C-R-E-S 25 at checkout on our website. I would also encourage you to sign the Student Climate Resolution. A group of students across Denver Public Schools have been working together to create a resolution for DPS to address the climate, sorry about the sweet toy, to address the climate crisis. Right now, DPS has no plan to address climate change and is not required to follow the City of Denver or Colorado's climate goals. The students believe that DPS needs to pass this resolution to address the climate crisis. I believe there are only about 75 signatures away, so you really can make an impact. If you are interested in supporting our students, the website to check that out is www.dpsclimateresolution.org. And with that, I will turn it over to you, Johnny. I'm sorry again if the screen's still acting up. I'll try to stop sharing and reshare and hope that it catches up.
No problem. Thanks, Lindsay. And hi, everyone. Thanks so much for joining us today. So I'm Johnny Rogers. I'm the Policy Director for the Denver chapter of CRES. Two sets of updates today. First, it was a very busy legislative session that just wrapped up about a week ago. At least 22 bills, by my count, passed that relate to climate and the environment. So keeping an eye on those to see which will end up getting signed by the governor, hopefully all of them. A few to pull out to be aware of that I'm pretty excited about. First, Senate Bill 21-261, encourage renewable energy generation, will create new opportunities for virtual net metering, meaning that a customer can build solar projects off of their site so they don't need to connect directly to their building and claim the credit for that solar to offset their use. This creates some really interesting opportunities for groups like local government, school districts, businesses that are interested in offsetting their carbon footprint. Those rules will probably take a year or two to write and get established at the Public Utilities Commission, but really, really exciting there. That bill also counts energy storage as a allowable distributed energy resource that can be funded with dollars from the Renewable Energy Standard Adjustment. So if you ever noticed on your Excel utility bill a 1% or 2% charge to the RESA, those dollars go towards funding solar programs, low-income energy efficiency, and now energy storage will be included in that as well. Jumping down the list, I also want to call attention to the two at the bottom, programs to reduce greenhouse gas emissions for utilities. A lot of these bills have really weird nomenclatures at the legislature, but it is what it is. The bottom two relate to gas utilities and gas-related programs. The first requires that by 2030, I think it's a 22% reduction in greenhouse gas emissions for all gas utilities in the state. And then the second requires those utilities to set more stringent targets for gas use reduction, and will create more funding for things like solar thermal and electrification, and just opportunities to better transition us away from our dependence on natural gas. All of these bills and more will unpack in our CRES Policy Night, which will be, I think, our first live event coming this September. The exact date and details to be determined, but really excited to be able to do that one live again. And I'll be reaching out to a couple special guests that will hopefully be able to join us to talk about the session and other things policy related in Colorado. Next slide. And there it is. So once laws get passed, they need to be implemented by the regulators. So a few things that are going on in the regulatory sphere right now. Xcel has filed its clean energy plan, which would get us to 80% renewable by 2030. That is just getting underway, probably a year's worth of proceedings ahead of us. We'll really be looking at things like how our energy efficiency programs and demand side management, things like rooftop solar and battery storage, and even electric vehicles being considered and incorporated into that plan. It calls for Comanche 3, the biggest coal plant in Xcel's fleet, to be the last one standing and retired by 2040. Hopefully we can get it retired even sooner than that and replacing it with cleaner energy resources. Additionally, there's an ongoing proceeding related to how the community solar bill credit is calculated. Over the past few years, the value of that solar credit has been being chipped away at. So it keeps getting less and less and less, which has been damaging to customers that have supported the community solar industry or have signed contracts to get that solar bill. We have some disagreement as to how that methodology, how that credit is calculated. We want to make sure that the value of solar is preserved so that we continue to support that in Colorado. There's also some groups that are working forward-looking regarding Xcel's programs. Xcel will be filing its next renewable energy standard plan later this year, trying to put a bigger emphasis on integrating storage in that plan and expanding more capacity and use of distributed energy resources. Also, its transportation electrification plan, which was approved earlier this year, actually implementing those programs, creating opportunities for people to get rebates for things like home EV charging and managed EV charging so that the time and duration of charging can best match with grid needs. Also looking at a program that would create opportunities for low-income residents to finance energy efficiency upgrades directly on their bill. They would actually save money based on that upgrade, and a portion of those savings would be used to pay back that investment in that equipment. So creating a lot more accessibility for those types of appliances, and doing so in a way that is accessible to renters, accessible to people who can't afford upfront costs of equipment investments, and just generally helping us with electrification and energy use reduction. And lastly, on demand response, as technologies get more intelligent, we want to make sure that they can be controlled. And as there are more electric vehicles, more battery systems, electric water heaters, or heat pump space heating, being able to control those high energy use appliances is going to be very important to match the intermittency of the renewable energy that we have on the system. The demand response will likely play a really important role in the grid of the future, and we need to make sure that we're making investments now that can prepare us to take advantage of those opportunities. With that, I will turn things back over to Lindsay and can't wait to listen to the presentation tonight. Thanks for the opportunity to give the update.
Jai, before you go, we actually have one question that's already popped up for you was any bill passed to clamp down on methane emissions and releases burning of methane?
So on that previous slide, the modernized demand-side management standards for gas utilities requires the utilities to calculate the methane impacts of their entire infrastructure. So putting much more emphasis on, the gas system has this methane intensity, and if we were to invest in an alternate technology, accounting for the social benefits of doing that. So methane, I think this is the first time that it will be accounted for in utility planning. So hopefully this creates a lot of opportunity for new investment and getting us off that system.
Great, thank you.
All right. Hi, everyone.
Perfect, thanks, Johnny. All right. So before we dive into the main event tonight, just two more quick announcements from me. So next month, we hope to see you back here. We are having Jessica Anderson, the Senior Resiliency Planner from the City and County of Denver's Parks and Recreation Department. I'm so excited to learn about Denver Parks sustainability programs. As Johnny mentioned, that will be online. So we know that certain things are opening up, but we are continuing our programming online through, at the very least, July and August to allow for everybody to continue to get vaccinated and to see how these larger live events go before we embrace those again. These virtual events also enable us to have speakers that may not be located in Colorado, which is a great benefit to us. So if you have any feedback about the fact that we're hoping to have a live event in September, please do email us. We'd love to hear from you. We are also planning on having a virtual streaming option, which we're looking into how to support, so that for those of you who do not yet feel ready to join us live, you will have the option to join via webinar. More to come on that as we get closer to that September go back to live date, but wanted to appease and addressing concerns that might be out there around that now. And without further ado, I am so very excited to get to our primary presentation tonight. I cannot wait to learn more about kinetic batteries and the journey to enable electrification for the masses. So big thank you to both of our speakers for joining us tonight. I will turn it over to you to do a brief introduction of yourselves, because you obviously will do that much better than I will ever be able to. But I'm so thankful for you both for being here, and I can't wait for your presentation. And with that, I will switch over presenter, and we will go ahead and get started.
Thank you, Lindsay. All right, so I'm Steve Milliren. I'm the co-founder of KineticCore Solutions, and I want to thank Ryan and Greg for inviting us to present, and especially thank Lindsay for her patience in getting us set up for the collaborative platform. So thank you so much. And with that, let's go to the next slide, please, James. So brief overview, just introductions. So I've introduced myself already. Our founder and CEO, James Clegern, please introduce yourself.
Good evening, everyone. My name is Dr. James Clegern, and we actually have a slide that gives a little bit of the background of both Steve and I's position with KineticCore, but we'll just zip through that when we get to it. And I'm pleased to be here to share some of this exciting information with you guys about a new capability that we are bringing on board.
So we promise to be brief, but James is a very accomplished aerospace engineer. I've grown up in the software and energy industry. So what I'd like to talk about is something that's near and dear to my heart, which is doing our part. When I say our, the founders, co-founders, employees, contractors of KineticCore Solutions, to accelerate the end of energy poverty. Energy poverty is really a bad thing. For example, as you look at this map, it looks like we have it under control in the Western Hemisphere. There's definitely some opportunities in Haiti and still some Central America, South America opportunities. But look at Africa, look at parts of Asia, North Korea. These people don't have access to energy. And depending on who you listen to, the current number of human beings that do not have access to electricity is about 13% of the population. We currently have, this was last week when I put this slide together, about 7.9 billion human beings on the planet. And by 2036, which lines up with a lot of the carbon goals for various countries, various corporations, we're supposed to have 9 billion people. So this is very important just for human survival, to be able to have water, food, shelter, and clean air. All of these human necessities rest upon reliable and clean energy. So it really does equal life. And I use these adjectives deliberately. So clean, I don't have to tell you guys about renewable energy and how clean it is, but reliable. In Texas, where I'm presenting from, we faced 6 days of rolling blackouts. You probably saw the news. And in February, we lost 150 Texans due to primarily hypothermia and $130 billion in productivity. So there's a lot of opportunity to improve not just the access to energy, but also the reliability of it. And of course, our vote is that the generation sources be clean as opposed to non-renewable and dirty. So let's take a quick look at the past 70 years in the United States. How have we been generating energy, and what are the trends? What are the limitations of certain energy or generation types versus others? So what I find extremely interesting is that hydro, deriving like the Hoover Dam, generating electricity from water flow, if there is water, that has remained very flat. And there's a reason for that, but primarily it's because it's very site specific, very expensive, and it relies on water. Kind of sad news last week about Lake Mead. Lake Mead is at the lowest point it's ever been. And this is with Las Vegas running at 50% capacity or less probably during our pandemic. Another energy source which is flattened out is nuclear. So what I really love about renewable energy is you can see the little triangle. If you can see you can't see my cursor, that's right. You can see James's cursor, but this emerging growth of solar and wind is good for everybody. I mean, it's not really debatable whether or not solar and wind are better for us in terms of quality of life and so forth. But look at the impact it's had on coal. The problem is when you sum coal and fossil gas together, you're still flat. So we haven't really begun to pull down in the United States our dependencies on burning fossil fuel, but we're getting there. Here's what we think we can do to help. So first little fact that probably all of you know, but I'm going to bring it up just in case, is energy storage is inherent to fossil fuel and nuclear. So if I were to compare a 50 kilowatt hour battery, for example, to a gallon of gas, they're roughly equal to each other. That gallon of gas is real easy to move around and transport in your car or burn anywhere. But the problem is it comes with a greenhouse gas consequence. So we see our part and it was touched on during John's section that there's more focus on storage, lots and lots of focus on energy storage. So for somebody to make a business decision in terms of do we generate with gas or coal, or do we generate with renewable, the cost of those, well, the existence of energy storage is necessary to support wind and solar, and I'll explain why. But the cost, the true cost of that energy storage must also be known to make a business decision, gas or coal versus renewable. But the other issue is this shows generation. What it does not show is rejected energy. So how sad is it when the wind is really gusting or the sun is really shining, but the demand doesn't line up with the supply and there's no energy storage available to match up those demands? What happens is the energy is rejected. And depending on the geography, sometimes those rejections are as high as 30%. The energy is just sent to ground. So to be able to go up against things that burn, we have to have renewable plus energy storage that has a true cost of storage that's known to quote unquote make the switch. So this is probably the #1 reason why KineticCore exists, is to be able to empower utilities, microgrids, corporations, charging stations, you name it, to be able to proliferate, excuse me, without necessarily big grid investment. So the lack of energy storage also has other risks. We had down here in Texas in February, we had several like pharmaceutical companies, people making medicine for dogs. When they lost power, they had to scrap much of their product. So reliable energy storage as it relates to continuous process, meaning that you don't have to scrap goods that are almost ready to ship, is also very important. So I'm going to go to an idealistic state at this point. So next slide, please, James. So I laid out these 4 categories that to me describe scalable, good, clean, the kind of energy storage that we should want to have. And I compared them against the current most popular, lithium ion, flow, which is, for example, using vanadium, which is a limited resource also, the traditional flywheel, which isn't perfect by any means, and then the ideal energy storage. So just a couple of points on this slide. When we consider the true cost of usage of something, we have to look at it horizontally. First, we have to look at mining. Does it require mining? If so, does it require a lot of water consumption to do the mining? The processing of the material, what does it cost to actually bring a battery to market? What does it cost to transport it? And how expensive or not is the site preparation? Is there a HVAC load? In other words, do the batteries need to be at 72 degrees Fahrenheit, regardless of the fact it was 120 yesterday in Phoenix, or in the winter, it'll be -60 in Anchorage? Do these batteries require a lot of TLC or HVAC? What does it cost to repair them? And one thing I really applaud the great state of Colorado on is you passed legislation that makes you a right to repair state. So literally in Colorado, people have a right to get spare parts and instructions on how to fix things, which makes them more sustainable. And on the note of sustainable, what's the life expectancy of the battery? Is it going to last for a couple of years, or is it going to last for 30 years? That's very important in terms of the overall cost of that usage. And then finally, recycling or disposal. So with lithium ion, it's great for mobility. And we feel that there's going to be tremendous demand for lithium ion batteries, which everything that you read in the news concurs with that. We think that stationary energy storage can be done better than with lithium ion. So we gave it a red. Flow, it gets a green. And I won't go through every example. It's not going to be 16 of these, but the ideal battery would have the lowest true cost of usage. Next row, scalability. So lithium ion is very scalable, and there's lots of it. And it can be manufactured in high volume, and it uses off-the-shelf components like the battery modules from Tesla as an example. And it's semi-picky about the site, but if you get the air conditioning and the heating, then site suitability is okay too. But you look at flow batteries and they lack some of the really important characteristics like material availability. Traditional flywheels, they are not made out of off-the-shelf components. Typically, they're like an engineered to order one-off type product, so they command a very high price. The ideal would score high in all these scalabilities. And then we get to performance. It needs to have a wide power range. So not to get too double E-ish here, but C rate is really important. If you look at some of the world's largest batteries, like down in Australia, they have a capacity of 4 times their max power. So if I were to have a 1 gigawatt hour battery made out of lithium, typically its maximum output is going to be 250 megawatts of max power, so that the battery can maintain its chemistries and its temperature. Flow batteries, they're great for long periods of time, but they're very low power. They run at very small fractions of what the overall energy capacity is. They are easy to extend, but they don't do high power. Traditional flywheels, same thing. They can do pretty good power, but they suffer with round trip efficiency, with mean time between repair, and then there's failures with some of the traditional flywheels. The ideal would have high scores in this category also. And then finally, the environmental impact. Is it born carbon negative? This is really important. I've researched what is the carbon debt of a lithium battery when it's born, and it's surprisingly high. So we would want to have one that is low, that perhaps captures carbon for its energy storage. We want it to be low water use. We want it to be non-toxic, recyclable, and repairable. So this is, in my opinion, the ideal energy storage. And I just wonder who can do this for us and where is he? And now I'd like to hand it over to Dr. James Clegern.
Thank you, Steve. Well, we'll kick it in. Steve gave a great overview of what the problem we're trying to address and what the ideal energy storage would be, especially with supporting renewable energy systems. And some of the greater scale of energy storage options that are available beyond the 3 examples that were given on the previous page is if you have a need for a high power capability, right now there's only a few options that can really do that, and they're very expensive. That's the section in the top part of this graph. If you're looking for long duration, you've got a lot of options and a very crowded market looking at longer duration capabilities in the 4 hours to 24-hour period. But what's missing is something that's affordable that'll give you the medium to high power range. And this is what KineticCore Solutions is really looking at, is bringing in our next generation flywheel capability to provide the medium to high power for applications. And these would be, we'll go through some of the applications a little more in detail in further slides, but this would be like, solar and wind smoothing, being able to do frequency regulation, be able to support hybrid EV chargers that provide high power throughput for quick charges. Those are all good examples that we just don't have a low cost solution, and that's where we are trying to come in and provide that capability. And this was hinted at a little bit before, but why not just use lithium ion? It's established, it's well understood, and the marketing folks says they can do everything. The challenge is when you are looking at long duration and maybe load shifting 1 or 2 cycles a day, lithium does great. And in fact, the kinetic batteries that we are developing are on par or a little bit more expensive in this low cycle, low power arena. But the challenge comes when you start using the batteries more often for peak load management, smoothing, grid regulation. The lithium batteries just can't keep up because they essentially wear out too fast. The harder you push them, the faster they wear out. And when they wear out fast, you got to replace them. Therefore, your continuing cost grows and grows and grows. Whereas with a kinetic battery that we're in the process of developing, you buy it once and it lasts for 30 years. You never end up replacing it. To really hit this home, you take this one example with peak load management, looking at 4 power cycles a day, and one kinetic battery is the equivalent of 8 lithium ion battery packs of the same capacity. So you end up having to do this replacement over and over, whereas going with a long life battery like ours, you don't have that reoccurring capital expense. So at a quick energy storage summary, This is a little more detailed than the slide that Steve provided earlier. As you can see, lithium ion has some great aspects, but it also has some negatives. Same with the flow batteries. And even the traditional flywheel has areas that they're really good at and other things that they are just do not do very well. What we are trying to do is produce a better, lower cost option that takes some of the best characteristics of the other battery sets and brings them into something that we can provide to the utilities, provide to commercial capabilities, and be able to bring on board and give you the better packaging of the new set of batteries. So you have the, it's not the lowest cost initial, but it's competitive. You know, we give excellent if you need high power, very good if you're looking at the long-term energy cost, long life, small footprint that we can package a large amount of energy. We're very good on the efficiency scale. And the big ones is that we are green and safe. Now, a lot of folks look at traditional flywheels and you think of, oh man, these big units. So really, to give you guys an appreciation, we're gonna do a little historical perspective on what has come before. So traditional flywheels have been in operation, and we look back over 2,000 years. And when you're looking at the earliest ones, that was the potter's wheel, where someone would be using their feet to push the wooden flywheel to provide smooth power for casting pots, clay pots. What clay pots don't like is pulses of stuff when someone's foot is hitting the flywheel, and it ruined their work. So flywheels have been traditionally used for power smoothing. And pretty much for the next 2,000 years, that's what they were used for, limited capabilities with regard to what materials you could put into play. But in the Industrial Revolution, you saw the massive improvement of metallurgy and allowing folks to make consistent steel flywheels, higher strength. With that, it allowed them to move up and be able to store larger amounts of energy per unit mass. That's what the specific energy is on our little graph. So the flywheels have had a steady improvement. And in the 1970s, you saw the modern era of flywheels coming into play with them incorporating high strength carbon composites. Again, improving the ability of the flywheel to hold energy and be suitable for not just power smoothing, but looking at being able to be a kinetic battery. The possibilities we're starting to show. The commonality of all these types of flywheels over the years previously is that they all are what we call a two-dimensional cylinder or disc. If you look at each one of these flywheels, it's a thin, a short or a tall cylinder in their design, in the structural design. Traditional flywheels that have emerged in the last pretty much 20 years. This kind of gives you a feel for what is being out there and what's available at the moment. If you notice, they are all cylindrical flywheels. They have stayed with the traditional design that was really perfected back in the 200 years ago in the Industrial Revolution. Their challenge is they are relatively low in energy storage capacity with regard to energy density, the watt hours per kilogram of the, that'd be our third column. And the hard part to get them adopted is that they are very expensive upfront per kilowatt hour. Now, they'll last you 20 years, but biting the bullet up front has been the #1 problem of traditional flywheels, is that it's very hard to fund your project when this type of energy storage costs this much. And some of the pros and cons, we've kind of touched on a few of these. Flywheels are excellent from a traditional standpoint if you want high power, long life with lots of power cycles. their overall cost of energy storage over their life period is very reasonable when you actually spread the cost out over their 20 or 30 years of operation. They have relatively good efficiencies, low maintenance, no hazardous materials with regard to chemicals that you have to worry about, and they have a pretty good temperature range of where they need to be able to operate. But the con side is their specific energy is very low, so they have to be massive, and that translates directly, mass directly translates to cost when you're getting these things built and deployed. They have high standby losses because they are massive and they require pretty hefty electromagnets or mechanical bearings to be able to operate. Apologize for the home defense unit that's barking in the background. They have issues with critical failure with regard to most of the folks, when they think of a steel flywheel, they think, oh, if it fails, you have high-speed metal shards flying out. Well, that is a detractor for a traditional flywheel, and that often requires them to have heavy shielding, where a lot of these would be potentially buried in concrete or steel vaults. And when you do have to service a traditional flywheel, it actually requires you to essentially disassemble the entire unit to get at the motor generator, which is tucked in right there along the shaft of this particular example. So it's a bit of a challenge to get at some of the parts you have to work with. And we've already talked about the high purchase cost is a detriment, as well as a 10,000-pound flywheel is a bit harder to deploy than a battery that you potentially could carry it by hand and stack up somewhere. So what we have come through with the KineticCore solution structural design is that we have a patented design that radically changes how the flywheel is physically built with the structure. If you take a look at the two pictures here, it doesn't look like a cylinder at all. It actually is a elliptical shape that is optimized with a blend of aerospace and mechanical designs to be able to give us incredibly better support and structural strength to go faster. So we basically address, like I had on the previous slide, all those cons. Our design pretty much addresses each one of those. It's an all carbon fiber design. So going back to Steve's comment of being carbon negative, congratulations. Our unit is about 500 pounds carbon negative. Because we have an all carbon structural design, carbon fiber structural design, we have no metal in the structure. Therefore, if we have a critical failure, we've been able to basically eliminate the high velocity metal shards failure mode that many people, that's immediately what they think of. Oh, it's going to kill everybody around it. It doesn't work that way. And the other positive piece is that allows you to be deployed without having to be buried. So it increases your deployment capability. The shape, like I mentioned before is an ellipsoid. And this curvature allows us to handle up to 50% higher stress. Then that translates to being able to go 50% faster speed-wise than our counterparts in the traditional flywheels. And this low mass, high-speed design, since I mentioned before, mass is directly related to cost. So if you have low mass, you end up with a low-cost system. And also, because we are low mass, our standby losses are significantly lower. Therefore, we can do a standby of 8 hours, 16 hours, and still have useful power to provide if the customer requires that capability. We can add additional storage by adding additional wraps on the flywheel itself. It strengthens the shell and allows us to optimize the mass, and we can actually make the flywheel a little more massive and a little less massive depending on the requirements of our customers. And the other big advantages of this design is the fact that we are able to shift all of our power systems to outside the vacuum enclosure to make maintenance extremely simplified and allows ease of cooling of the electronics. Whereas Before, if you looked at the standard design, all the electronics for the motor generator and all the pieces are buried deep inside the flywheel structure itself. And by being able to pull them out and being able to access them, it makes simplification of the maintenance and operations much, much more appropriate and easier to apply. So the results of our design approach, if you remember that earlier graphic where I had the evolution of the flywheel, traditional flywheel with the new materials, it allows us literally to give a factor of 10 jump in how much energy we can store per unit mass, and puts us right in the capacity of competing with lithium ion because they're in the same region with regard to energy density. And the advantages here, and there we go, there's a picture of the traditional flywheel versus our prototype that we finished testing last November. When we have the access to additional or improved commercial composites, that can be wrapped in, literally wrapped into our design, and we can advance the capabilities, and we have a continued upgrade path as more advanced composites become available and the prices drop. We can incorporate them right into the design and increase our capabilities. So our overall system approach is to drop the front cost down. So if you take a look at our traditional flywheel, this is an example. You know, we are looking at a lower cost on materials, a longer service life. So when you buy it, you can expect a 30-year operational life out of the unit. A lot of our subsystems are commercial off the shelf, where we can basically use a electric vehicle's motor generator. As you can see how it's mounted above our flywheel there. That's a commercial off-the-shelf unit, whereas a traditional flywheel, that's a custom one that is tucked up inside the flywheel structure itself. Our system also lends itself to being able to be set up in an assembly line, so we can get the advantage of mass production. Placement, all we need to have is when we get our system placed out to the customer site is a level concrete pad and no vaults. So all these pieces really translate down into an initial cost that now becomes competitive with lithium ion versus for an upfront cost versus the traditional ones that are just very, very expensive and can be used for special events, special purposes that they need to have. And overall, the levelized cost of energy storage, we come down to, we're talking $3 to $8 per megawatt hour, which combined with a renewable power source makes us directly competitive with even the best natural gas combined, peaker plants for energy generation. So you now have a capability to make renewables available 24/7 with cost-effective energy storage. And there we go. The traditional units, special projects is what they could be used for. We are now cost competitive, and it gives you the ability to have cost-effective energy storage to be paired up with. Our upcoming product, because we are in prototyping right now, is bringing on board this type of a system where we have a sealed flywheel paired with external power subsystems to give you a kinetic battery that's approximately a 5-foot footprint and is able to support 50 kilowatt hours in that little box with a 25 to 250 kilowatt range, depending on the motor generator you pick to apply. And here's some of the specifics under there. Patented design. We really focus on commercial off-the-shelf parts to keep the costs low. And the unit is scalable up to multiple megawatts because all you do is stack the units next to each other and you just add the number that you need to support your application. And the big advantage is we are now deployable to whatever site you need to have us to be able to provide access to. So some of the markets, we've kind of touched on this a little bit, but in the regulatory and the utility arena, we are very effective in supporting peak load handling and regulation, as in frequency regulation. And so we're in discussions with quite a few of the utility companies, and actually, especially in Europe, who are very interested in being able to apply this capability to support their peaker plants that they're looking at bringing offline, or decommissioning, I should say is a better term. The other area is with our renewable teams being able to provide a load smoothing, because as we have more renewables penetrating the markets with regard to providing power to the local grids, the requirement for them to provide a smooth power flow coming in is going to grow and grow. And it also allows us the capability of capturing overproduction if the demand is not there to take what they can put out. Energy storage allows you to capture all the pieces. And our third major market area is actually supporting the capability and expansion of electric vehicles by providing a high power hybrid charger that allows you to be able to get a 15-minute quick charge anywhere. All we need is a level 2 power access to the grid, and we can provide a extremely good and high charge all the way up to a Class 8 semi-truck electric vehicle. And down the road, once we get the design and the producibility and get the advantage of bringing the costs down, well, commercial and residential are also areas that we can come in to provide support with regard to reducing utility bills, doing peak load management, and other areas. So the next 3 slides, and then we are very close to the end here, is, well, that's great. I love the idea of a next generation kinetic battery, but why does it matter? Well, the first example is what we touched on earlier about, well, what about the possibility of a peaker plant replacement? So natural gas turbines or peaker plants, when they are only utilized for, spinning reserve and supplying support to, like, say, renewables, it costs between about $69 and $107 per megawatt hour to provide that pulse load capability when they're only being utilized 20 or 30% of their overall life, usage for the day. But each one of those things, for every megawatt, you're generating almost a ton of CO2 to provide that peaker support. So back in 2015, Beacon Power, which was one of the traditional flywheels, said, hey, we can make a peaker facility that, we don't generate any carbon dioxide. But they were very expensive. They have 2 sites out in the New England area. As you can see, they almost were cost effective to be able to make a profit while operating, but they're still pretty expensive. Then in 2018, we had the big facility that Tesla put in place in Victoria, Australia. Give them credit, it was designed to capture solar and shift 4 hours of solar from the middle of the day to, like, say, 4 hours in the evening. But just looking at what it could do, it's still expensive for doing 1 cycle per day. And goodness, if they tried to do regulation with it as a peaker plant, it becomes really expensive because it requires frequent battery replacements. But in some aspects, it's better than the traditional flywheels, but in other aspects, it's not. When we bring our projected capability on board, maybe about 2024, that's when we'll be ramping up the full rate production. we are able to effectively provide a peaker plant replacement that is cost effective. So a customer putting this into play would actually make money off the system and be able to proliferate the capability as a replacement for peaker plants, especially when paired with renewable systems providing the base power. You have a very good combination. There we go. There's your price when you combine this with solar or wind and tack on the cost of the storage. You're right at $35 to $39 per megawatt hour, well under the cost of a traditional peaker plant for natural gas. All right, another why does it matter? I had to pick one renewable, so we took a wind example. The graph to the left shows what happens when you're don't have energy storage with your wind farm. You have periods where overproduction is lost, and if you are underproducing what is expected for the demand, you have to have it filled in by those peaker plants. That's what the red stands for. But if you have adequate energy storage, you can store the overage and use it to fill in the areas that you are coming in under, to level things off and reuse that power and give you the potential of earning a lot more for what you're working through. So what this actually translates to is we use the hypothetical example of a capability that's like a 100 megawatt or 90 megawatt wind farm. It's generating approximately 1,500 megawatt hours per day. And with using that graph on the left, you lose about 300 due to overgeneration that can't be utilized on the grid. And you had to buy 100 megawatts worth to fill in the gaps. And so your overall revenue using that model is about $33,000 per day that the wind farm can generate. Well, you could put in lithium ion, and it is very much a viable energy storage capability, but with the high loads that we'd be looking at supporting the wind farm with, it requires a much higher levelized storage cost to be able to support that application. So you do generate a nice daily revenue, but it actually ends up being a little less than with no storage because of the high power requirements of handling the drops and the capabilities that the wind is putting out. But when you bring the Kinetic battery on board that has that ability to handle high power, our levelized storage cost is much smaller, and you actually end up being able to realize a higher daily revenue. And in this particular case, you're looking at almost a 70% increase by providing the smooth, by capturing overproduction, filling in the gaps when you're underproducing for the demand. And as a side bonus, you're providing smooth power to the grid, so you met that upcoming requirement that most providers are going to be requiring from anybody producing renewables. And our last example of why does it matter that we hinted at earlier was boosting EV charging. Most of the folks out there really want to have convenient access to high power that can get them charged fast. The challenge is the grid is not set up to have a lot of high powered chargers active, especially if you have a bunch of them together. You have the tendency to brown out your local grid and make the local neighbors unhappy when someone is putting in a whole lot of high powered chargers. With being able to bring in our Kinetic batteries as a energy storage that is paired with a high powered charger, it allows you to access a smaller amount of power from the grid, store it, and when an EV comes up, you can provide them a very high powered charge where their energy storage combines with the level 3 charger and can provide a larger capability. This really becomes important when you're looking at folks pulling up to request a quick charge, because It allows you to provide that at a almost 50% lower cost because the power is cheaper, the infrastructure is cheaper, and than a traditional level 3. And the other big advantage is that a level 2 grid power access, that's basically a 220 volt, 100 amp or so, is much more readily available for where you could place this type of system, increasing the convenience aspect of being able to be deployed almost anywhere. And the other advantage of having our type of battery versus, like, say, a lithium battery pack is that we last for 30 years. So you buy us once and you never have to replace the batteries. And it also ends up with for a moderately busy charging station, an ROI of under 2 years. And what it really ends up being is that if you can get more of the hybrid charging stations out there, it gives the convenience factor, which this particular graph down here shows that EV owners, 55% want the convenience of a fast charge. They don't want to wait 4 to 6 hours to charge their car up if they're in the middle of running around the city or going on a trip. So convenience becomes a really big factor of adoption for EVs. The second most important one is the fact that they don't want to pay through the nose for a quick charge. They want a lower cost. So 25% of them is really important what the cost is going to be. So both of these combined together gives you the ability to increase EV adoption by providing the convenience and the lower cost in a package. And so in quick summary, energy and energy storage is truly a global issue. We have the means to potentially help address that. We come in with the market out there of what is required for doing, and we become a very cost competitive option in the mid to high power range that most of the chemical batteries just really can't handle, both from a capabilities and a cost standpoint. And we actually combine a lot of the positive characteristics of a chemical and a traditional kinetic battery into a package that has some of the best aspects of both sets of storage capacities. And we kind of walk through some of the limitations of a traditional design and how our innovative design that basically addresses all of those and provides a solution path to make it more effective and affordable and deployable. And we have a whole bunch of really good markets that are looking to pull in the capability by having this medium to high power capability. And as a quick summary, we are not designed to do the long duration power storage like traditional chemical batteries are really good at. We don't want to compete with them there, so we're not. Chemical batteries do great in the 4-hour to 24-hour long duration time frame. We are specifically looking at the 2-hour to 12-minute duration time frame of the medium to high power. And we have plenty of markets that are looking at doing that, and we enable amazing amounts of capability, especially in the renewable arena. And last but not least, thank you guys for your time. We appreciate the opportunity to come out and talk. And a little environmental note. Each one of our 50 kilowatt hour Kinetic batteries operated over its 30-year life can store and dispense up to 10 gigawatt hours of renewable energy when we're paired with solar or wind. And this has the impact of literally being able to have planted over 8,000 acres of new forest for being able to do carbon consumption and containment. We paired up with EVs. We're looking at over 500,000 gallons of fuel by being able to rapidly charge the EVs when folks need a rapid charge instead of them relying on a traditional gasoline or diesel truck to be able to go the distance that they want to go. It also, by having our battery in place, we deferred the equivalent of 21 tons of lithium ion batteries over a 30-year life. And this also translates into the over 200,000 gallons of water that is used in mining the lithium for those batteries. And last two items are really near and dear to our heart with regard to one battery is effectively being able to remove 22 megatons of carbon dioxide when we're paired with when we are paired with renewables. And top it all off, not as big a deal here yet in the United States, but very much a big deal in Canada and Europe, is one battery can basically generate the equivalent of over $1 million worth of carbon credits from being able to do renewable overproduction capture. So leave that with you guys as a parting note, because it has some amazing green implications. And we look forward to answering any questions that you all might have, or if I've gone over my time, we can field some later. Thank you.
Thank you so much for that lovely presentation. It was very interesting to learn about this. It seems like such a great technology. We've got a bunch of different questions from our members. If you have a few more minutes here.
Sure.
Great. So the first one, I know you talked a lot about the implications of this technology and replacing like larger scale operations, but are the batteries installable in a home environment and compatible with solar panels? Are they within the reach of a homeowner price-wise?
At the moment, we are geared up for building the larger style battery, the 50 kilowatt hours. Most homes, unless you have a larger, 3,000 square foot or larger home, you don't use that much power over the course of a day. So the price points are more suited for large scale deployments at this point in time. But like I alluded to, when we're getting ready to once we reach full rate production approximately in 2024, and we get the system, get the economies of scale for mass production, you might end up with if the demand is there, a smaller version of the flywheel can be generated that would be more appropriate for a homeowner to be able to pair with the side of their house. And you're looking at, it'd be the equivalent of buying like a new air conditioning unit. You need your concrete pad, you place it out there, you hook it up to the power. And if you have solar, you charge your flywheel the entire day. And then if you have any of the high power requirements at the household or the evening power is being used, we can discharge in that type of cycle. And the other advantage is that because it's a larger battery capability, it provides the option of actually a whole house uninterruptible power supply. So if you ever go out of power, you have that capability of backup power for a day, maybe two, depending on how you use it.
Great, thank you. And then I know that you spoke to the EV charging speed to actually charge the car, but we've got a question here about how quickly the KineticCore battery can be recharged between EV charging cycles.
An example would be for a moderately used but low power access, grid access level 3 charger that we're paired with. You would look at a 2-hour recharge, and then an EV would pull up and we'd be able to give them a 50 kilowatt hour quick charge in 15 minutes. So that's the type of thing. But as the demand goes up, if the grid access improves, you can step up with the power that's coming into us so that it shortens our recharge cycle from 2 hours to 1 hour to maybe a half hour, and then we can ramp up how many recharges that we can provide.
Great, thank you. All right, the next question here is about the sound output. Basically asking how noisy are the flywheels?
Oh, if any of you have been surprised by someone driving a Tesla driving up next to you and you hear nothing until it's literally driving by, that's essentially the noise level that we are looking at, because our system is a vacuum enclosed flywheel. So other than some vibration that you might have, there is no noise that translates out. And the motor generator that we use is the same one that goes in a Tesla, essentially. So very quiet, sits on the side of your application, and the worst case you might have is if you're leaning up against it, you might feel a slight vibration in the box.
Great, thank you. All right, the next question here is, lithium batteries are dependent upon a supply of rare earth materials. This could be a challenge, of course, in the future for lithium-ion batteries. Are your composite materials similarly dependent upon these rare earth minerals or rare earth materials?
That's a good engineering answer is it depends. The majority of what we build the flywheel out of is 500 pounds of carbon fiber, which is not required to have any rare earth minerals in it at all. The place that we do have some of the rare earth minerals is about 20 pounds worth of permanent magnets that are used within the system. But 20 pounds of niobium magnets for the high-powered permanent magnets compared to 800 pounds of lithium, cobalt, nickel that goes into the equivalently sized lithium battery pack. We're doing our best to minimize what's required there for a rare earth access.
Thank you. All right. Next question is about actually there's two here about the ellipsoid shape. So the comment before the question is, the use of the ellipsis shape seems to go against the rotational inertia of the shape versus a disc or disc with rim only. So a few questions here. How can it therefore store more energy? Is it because it can be spun faster without risk of failure than a disc? And why is it hollow? Why not put more mass in it to store energy?
All right, very good questions all the way across the board. The amount of mass, and like the gentleman or our questioner said, the inertial mass of the unit compared to the traditional flywheel and ours, when you're looking at something built with a cylinder of the same mass that we are, the moment of inertia is almost identical. We're about 10% better because we are able to put a lot of the mass out further in radius, therefore it's more efficient. And then the other major portion is the elliptical design with how we wrap the elliptical flywheel. It's a lot like when you would wrap a pressure tank. If anybody's familiar with fiber wound pressure tanks that are used by the firefighters and stuff, the advantage of the elliptical shape is that it allows you to handle higher stress. In other words, you don't need as much material. And that higher stress also allows us to spin faster in that particular shape design. So a traditional flywheel is limited by its two-dimensional shape, you could say, and is also limited by the strength of the steel, where it is connected to like a hybrid cylinder of carbon fiber that they've wrapped around it in a big circle, or a solid steel flywheel all by itself. The steel is the limiting factor of a lot of the design, and we have been able to eliminate that particular issue and allow us to spin much faster and store more energy for a smaller amount of mass.
Right, thank you so much. Got some technical folks on here who are eager to jump into it. Here's another technical question, a few numbers, so bear with me as I read through this.
That's fine.
So one of our members says, I think you said that the energy density of your flywheel was comparable to lithium ion. One can buy a 2,000 kilowatt hour, 2-hour lithium battery in a 20-foot container, which is over 15 kilowatts per square foot. Your unit has a footprint of 2 kilowatts per square foot. So how can you compete in the 2-hour storage market segment? And let me know if you need me to repeat that.
Well, again, there's a lot of it depends. Our units are stackable too high. So you actually end up doubling what he quickly calculated there. We are, for this same size box, the same lithium capability of 50 kilowatt hours roughly fits in the same footprint as our system. When you actually go and compare like a Tesla Megapack out there, they're roughly the same packaging, but they can stack theirs, 8 feet high, and our system we can stack 2 on top of each other. So it does give you that capability, but the true measure of how much energy is packaged in the square footage, it all comes down to how you package it as well. If they are putting the lithium battery packs in a steel container, a 20-foot container, now you're looking at something that probably weighs twice what we weigh, but may have a little bit better edge on us with regard to energy storage per square foot.
And James, I'd just like to add one quick thing. We do not require nearly as much HVAC footprint nor fire suppression. And also, because of the fire that happened in Arizona, there is increasingly separation of lithium ion modules. So I'm going to take for granted, I'll take the person's word about the energy density, but I know that we can be just purely laid on the slabs, and we don't need all the other footprint that lithium ion needs.
That's great. Thank you.
Sure. Yeah, our system is able to be deployed, it'll operate minus 40 degrees all the way up to 140. So we can be in Alaska during the winter, and we can be, well, almost in Death Valley, but I really wouldn't want to operate anybody's battery in Death Valley if I can avoid it.
Great, thank you. All right, I've got a bunch more questions here, so I'll try to go quickly through them. How do you know the product will last 30 years?
Well, a lot of our traditional flywheels are already been in the 10 to 15 year. Some of them are advertising 20 years. Some of the other traditional flywheels, like your traditional windmill in Denmark, they've been effectively in operation for over 200 years. But as with any other system, you need to make sure that they have their routine maintenance. And the advantage of ours is the fact that the maintenance is actually very simple, and also that we do remote monitoring to be able to track what the system is being able to do, and if it requires any more immediate maintenance other than the traditional level 1 stuff.
Great. All right, thank you. Next question here is, does ground movement, earthquakes, traffic, etc., affect it?
Sorry, could you repeat that? You were a little broken up.
It was earthquake rating, James.
Oh, earthquake rating.
Did I get that right, Lindsay? Oh, we lost Lindsay. I believe the question had to do.
I'm turning off my video just so that my interconnection is a little better here. So hopefully you guys can hear me now. Does ground movement such as earthquakes or traffic affect the battery is the question. Yeah.
Okay, well, the quick answer to that is, is the system is designed to be able to be deployed to a class 4 arena for structural support. So that pretty much means we can handle, everything that the design is capable of handling it. And as we go into building our units, we'll actually take them and put them on a shaker table and give you what it really can do. The bearings and the magnetic support system and everything else is designed to be able to handle, up to literally a class 6 seismic event and survive. But if it detects one of those, the advantage of remote monitoring is that you would power down gracefully and have somebody come out and check it if you're getting some kind of a earthquake of that magnitude. But in theory, yes, that it will be able to pass a seismic test rating and be able to be deployed like in California.
That's great. This next question is very related to that. So how is the safety of the Kinetic battery evaluated by larger purchasers like GSA?
The first items that we'd be going through would be getting Underwriter Labs equivalent certified. The advantages that we have using off-the-shelf components like our motor generators, they've already been certified. They're already in place and used in EVs. So that would be the first path that we would go through to get the basic certifications. And that's on our planning docket for as we get to that point. And being able to get certified for the seismic events, again, requires you to actually go to a testing facility where they shake you. And then if you are able to survive the different levels of magnitude they put you through on the test, you get the appropriate rating at that time.
Right? Perfect. All right. 3 more questions here, and then we'll let you guys get on with your evening. But the third to last question, could you explain a little bit more about how these batteries are carbon negative?
All right. The fabrication of the carbon fiber that we use for the structural wrapping of the flywheel itself is based, it's essentially a petroleum byproduct with carbon dioxide that is used within the manufacturing of the fiber components, the fiber strands, which are then wrapped into the what they call the fiber toes that we then use to wrap the structure of the flywheel. So we have literally 500 pounds of carbon composite already in place that has captured that carbon footprint, you could say. So from that standpoint, that's where we're saying we already have that in the package from the start. But the rest of the pieces is really with us being paired with renewable energy, and that's where we can allow them to become even more carbon negative with regard to capturing the excess power generated by the renewables and making them basically available 24/7. So the renewables, instead of being a intermittent resource, they become a continuous on-demand resource.
Great. And a quick follow-up to that is, doesn't petroleum byproduct mean that it is dependent on petroleum production? Is the carbon intensity of the petroleum dependency accounted for?
Oh, so much of what we make right now, and we have usage-wise, our plastics and all this other stuff is all, is based on petroleum. The being able to make fiber composites from non-petroleum based pan products, I'd actually have to go talk with our team that works a lot of those things a little bit more to give you a better answer on that.
Okay, got it. All right, second to last question here. Have you explored applications of your flywheel as a reaction wheel or gyroscope?
Oh, by definition, our flywheel is a reaction wheel and a gyroscope. But no, not from the applications for like stabilizing boats, aircraft, spacecraft. Those are more specialty applications and really require something that's a much smaller footprint than what we're looking at doing. And other than it would be neat to work in that arena, not really the form factor that we're looking at working with at this point in time.
Excuse me, James, just one minor exception would be we'd have thought about electric locomotives, and instead of all that regeneration going to heat, the regeneration can go to RPM. But by being able to play with which side counterclockwise or clockwise is spinning faster, the train could hug the turn a little bit to improve the performance of the train. That's the only gyro example I remember. that I was discussing.
And that was one of the examples for the high-speed trains that multiple communities in the United States are exploring putting into place. And that could be an application where that feature can be used as a side bonus.
Great, well, thank you. And then we'll end it with this last question for you. At what point will this become commercially available?
We are planning to go into pilot production next year and are actively securing strategic partners that want to have pilot sites to be able to use the first couple hundred units. Then we'll be going, the plan is for low rate production in 2023 to 24, and then full rate production in approximately 2024. So there'll be, those wishing to do advance orders, they get in with the earlier ones, of course, but being able to be available for mass production would be looking at 2024.
Fantastic, thank you. So big thanks and round of applause to you, Dr. James Clegern and Steve Milliren. Thank you so much for joining us and for presenting to us. I'd also like to extend a thank you to our members for listening and for the engaging questions. Looking forward to hearing updates about KineticCore as your journey progresses. Thank you again for joining us here tonight, and best of luck moving forward.
Very much for having us. I appreciate it and enjoyed the presentation and being able to give it. Have a good one.
Yes. Thank you, Lindsay.
Thank you too. Bye.
Great night.